Hey everybody, we're going to do our first set of notes here in physics. We actually start in chapter 2. I want to encourage you inside of Notability to add a new divider and call that divider physics. And after you do that, let me get out of this because I don't want it. Inside of your new divider, once you're inside of physics, I would suggest that you add a new subject and call it physics chapter 2 just to keep yourself organized, and then get your notes from Schoology or Google Drive, wherever we post the notes, and open them up. And let's go ahead and get started. So in lesson 2-1, we're going to talk about motion in a straight line. Here are all the objectives. You can read through them. We're going to kind of talk about we're going to treat everything like a particle, a point-like product. We're going to talk about the difference between position and displacement. We're going to talk about average velocity. We're going to talk about average speed, the difference between speed and velocity. And we're going to talk about looking at a position graph. But before we begin, let's start and talk about this fancy word, kinematics. This can't this word kinematics is the definition. It is the classification and comparison of motion. So let's go ahead and fill that in. The classification and comparison of motion. So oops, I didn't spell motion right. You would think I'd be embarrassed, but I'm really not. So whenever you hear the word kinematics, we are talking about moving items. There's going to be so much kinematics in physics. Let's go ahead. Now we are going to follow these three general restrictions. First restriction, the motion today is along a straight line only. We will discuss other things eventually, but right now we're just going to talk about motion in a straight line. This line may be horizontal, vertical, or diagonal. All right, I know we're getting the boring stuff out of the way. Number two, you need to understand that forces, whether a force is a push or a pull, that causes motion. Forces, whether it's a push or a pull, causes motion. And number three, excuse me, please. The moving piece is a particle or behaves like a particle. So whatever we're talking about. Oops. Or behaves like a particle. And we're going to assume that all particles move at the same rate. So we are not currently concerned, like if we're talking about a person, we're talking about the person like they're just as a dot in space, not like its hands separate from its foot, from its legs, from, the legs moving at a different speed than the head, just one particular particle. We're going to treat everything as. Now, when we talk about position and displacement, we need to make sure you understand origin. Origin is the reference point. Typically, we call that 0, so I'll put normally 0. And if you move in the positive direction, you're talking about movement to the right of the origin. And if we're talking about a negative direction, we are talking to the left of the origin. Okay, so if we start here on 0, we will call this origin. This way would be positive. This way would be negative. Okay? Now, those are always that's like the basics, the startup. I'm flipping my page. I have my answer key next to me because nobody wants me to screw up. Let's say that we have a particle, and that particle is at a position of -5 meters at a seconds, well, I should say seconds behind it, of 0. And then at x equals 2, so it's at a new position. X1 is the first position, x2 is a new position. It is now at 6 meters, and it has elapsed for 4 seconds. Interpret each of these positions with respect to the origin. All I want you to be able to understand about x1, the -5 meters, is that it is 5 meters to the left of the origin, and that the positive 6 meters is 6 meters to the right of the origin. Ooh, physics is easy so far, right, guys? Yeah. Okay. Now, the ability to describe the position of an object allows us to ask questions about change. With this change comes two different types of quantities. Now, something I will encourage you to do, remember, physics is still a little new to me as well. Obviously, I took it in high school, I took it in college, and I studied real hard last semester or last year, summer so I can pass my physics test, and I taught it last year. However, I'm still learning. Every time I teach physics, I think I'm going to learn something else. So, with that being said, when you see these little helpful videos, those videos are videos that I have watched that I have found to be beneficial for me. Everything that I do in preparation for notes is probably something you want to look over too, because if your teacher is preparing that way, it's probably a good idea for you to also have your head preparing that way. All right, so there are two things. There are scalars, which are a little more simple, and then vectors, which are a little more involved. So if we are talking about a scalar item, we're just talking about the magnitude. Like how big is it? Magnitude. All right. Now, if something is a vector, it has a magnitude, like a size to it, but it also has a direction to it. All right. And what you should probably do, watch that video. He's going to talk about differences between magnitudes and vectors. All right, let's talk about distance. Distance, let's say like I go home, right? I go home to my house. I get in my car and I drive home. Distance is the full path that an object travels. I think I've been teaching here for 13 years. You would think that I know. I feel like I live about 14 and a half miles like from school. Like, and considering I do lots of turns, I go on 18, I go on Green Garden Road. Um, but like it's about 14 and a half miles to my home. However, the displacement is much different. The displacement is the change in position from x1 to x2. Like if I could go in a straight line, how about that? So I'll say the change in position from x1 to x2. Now, displacement can be negative. Distance is not. So displacement, you could say left, right, up, down. Distance is just a value, how far something has gone. Again, there's another helpful video. I would absolutely watch it. If I'm taking the time to put those links in these documents for you, you should take the time to pause the video and watch them. All right, let's talk about displacement. Now, some of you are familiar with this triangle X, right? And any of you who are familiar with that, you're wondering why I'm using the word triangle X. That's because that triangle is red delta. Okay? So what does that mean? Delta is a word that means change in. So this is the change in x being my position. So displacement is the change in my x placements. So I would take my final placement, x2, subtract my original placement of what I was discussing, in this case x1, and you would subtract them. So by definition, displacement is x2 minus x1. Let's take a look at example 2 to talk about the difference between distance and displacement. Calculate the distance and the displacement for a trip from your friend's house to the grocery store and then back to your house. So we are going to start at, let's see, the displacement from a trip from your friend's house. So we're going to start here, and then we're going to go to the grocery store. Whee! And then we're going to go to your house. Whee! Let's talk about the distance. So when I think about distance, when I go from your friend's house to the grocery store, that is a distance of 2.1 and 4.3. And then I have to go back to your house. So that's another 4.3. So let me see if I can change this part right here. So I'm going to go from your friend's house, I'm going to go to the grocery store, and then I'm going to go to your house. So that's 2, 1, 4, 3, and 4, 3 for a total of 10.7. That's a lot of walking. That's your distance. It's how far you have physically walked, whether it's positive or negative. Now let's talk about displacement. Displacement is only concerned with the change in your x position. So that's like saying, what is your final position minus your original position? Okay, so your final position is 2.1. So if you consider this 0, so like maybe I need to make sure I emphasize this. Here's your original starting position, right? And then you end here at 2.1, and way out here would have been whatever 2.1 plus 4.3 is, so 6.4. Okay, that's what you need to think of. So if this is 0 and this is 2.1 and this is 6.4, your displacement is your final position, which you're ending up at your house, right? Your house at 2.1 minus your original position, which is your friend's house, of 0. So your displacement is 2.1 miles. Now, if you think of that, hopefully that resonates and makes some sense. Like, I know you've gone a lot farther than 2.1 miles, but from your beginning spot to your ending spot, if those are the only two things that you considered, you've moved to the right, to the positive direction, 2.1 miles. Hopefully that was okay for you. Now let's take a look at the difference between average speed and average velocity. They are much different than each other. Speed and velocity, I mean, a lot of times we think of those as being the same, but they're not, okay? Speed deals with distance. Let's go ahead and just simplify this now. Speed deals with distance, velocity deals with displacement, okay? So they're both concerned about the time as well, but speed is distance, velocity is displacements. Once we describe motion, we want to consider how rapidly does an object move. So let's talk about average speed first. Average speed, notice I wrote it with like speed and a little average symbol down there, or a little average subtitle, is your total distance. So in the last problem, that would have been, what was it, 10.7, divided by the total time it takes you for whatever specific time frame you're looking at. And that right there, there's a nice little formula for you. So let's go ahead and just use distance. If you don't mind, let's go ahead and I was going to do x if that's okay with you. X is how far you move. Maybe I'll just use d for distance, okay? And then divide it by time. That might be better for you. I hesitate to use s for speed because eventually s might stand for something else. So I'll actually write the word speed. So if we know that the average speed is equal to the distance over the time, what three equations will we can make from this? Well, the first equation is this equation. And a good algebra student would be able to move the t to the other side by multiplying by it. So we could say time times speed average, or average speed, equals distance. And Another good algebra student would be able to solve for t by dividing by the average speed. So we could say time is the distance divided by the average speed. That's called literal equations, manipulating literal equations. You learned that back in Algebra 1. So just manipulating our formula. All right, let's take a look at example 3. Now, this link isn't that fancy. It's just we can even watch it. It's a video of a king, what are they called? A kingfisher bird. Whee, here it goes. Oh, it's a very, here you go. Ready to watch your bird dive? Oh, I'm really hoping you guys can hear the music. Whee! It's very peaceful music if you can't hear it. Anyway, woo, there's the picture for you of the fish of the kingfisher bird that can catch a fish by plunging into the water from a height of several meters. So it's like way up top, it's looking and sees a fish and it's like boom. If the kingfisher dives from a height of 7 meters with an average speed of 4 meters per second, how long does it take? So we got to figure out long. So it's asking about time. So what I'm going to do here, I'm going to label what I know. I know that it's going to travel a distance of 7 meters. I don't care that it's going down 7 meters. I'm not going to use a negative because it's about distance and average speed. I'm going to write that my average speed is 4 meters a second, 0.00, but I'm not going to write that. And I'm going to write that my t is unknown. Now, right now, you're probably thinking, Mrs. Langeli, I can do that without labeling everything. Fantastic, good. But you're going to get to a point in physics where like you're going to have like 20 variables and you're going to need to label a lot. So let's just start good habits now. All right, so here we go. How long? Since we don't know t, I'll do t equals, I'll use my third equation up here, d over speed average. Really, I should say average speed. So my distance is 7 over my average speed is 4. I conveniently have my calculator app available. It's almost like I thought about it before I did my notes. 7 divided by 4. I'm going to use all those decimals. I get 1 point. They don't tell me what to round to, I think. So I get 1.75, and since this is seconds because it's in time. Now, if you don't believe me that it's in seconds, it's meters divided by meters per second. So the meters cancel out, you end up with a second. All right. In many situations, there's a quantity that's even more useful than the average speed, and it's the average velocity. Hey, look, guys, another helpful video that your math teacher had to use, or your physics teacher had to use. It must be about average velocity. And what that video is, it's a guy, and you might need to slow it down because he has an accent. It's hard to understand sometimes. But like if you slow it down, you listen to him, he does a fantastic job. It's almost like my car scenario, like where I might go 14.5 miles home, but really if it was a straight line, it would be different. So let's talk about average velocity. Average velocity is the ratio of the displacement to the change in time. The ratio, math students, you should be thinking fraction of the displacement or to the change in time. All right, so we should be thinking of a fraction when we hear the word ratio. It's almost like a slope. Just giving you a hint that's important. Average velocity, again, average velocity is concerned with the beginning and the end position of a time frame. Average velocity is the change in position, delta x, over how much time it takes, so delta t. You could just probably put time there. And I mean, like, t is going to stand for how long it's been. So if we wanted to, and this is displacement, right? Didn't we talk about this is displacement instead of distance? So that would be x2 minus x1 over the time associated with x2 minus the time associated with time 1. All right, let's go ahead and take a look. Example 4. An athlete sprints 5 meters in 8 seconds. He stops, and then he walks slowly back to the starting line in 40 seconds. If the sprint direction is taken to be positive, what are the average sprint velocity, the average walking velocity, and the average velocity for the complete round trip. So I have it nice and spread out here for you. Let's find the average sprint velocity. So we know that the average velocity is equal to, so we need to look at his sprinting, like how far did he go? Well, he started at 0. He started here at 0, this orange dot I'm making, and he went to 50. So we're going to do 50 minus 0. And how long? So it took him 8 seconds. Oops, I did that backwards. It took him 8 seconds to make this trip, minus we started at t equals 0. So we get 50 over 8. And when we divide that, we have a beautiful 6.25 meters per second. Okay? So that's his average sprint velocity throughout the whole thing. Maybe he sped up, maybe he slowed down, but that was his overall velocity. Now let's do the walking velocity. All right. So for the walking velocity, so velocity average, you know what? I'm even going to put walking here just to really give it some good labels. I am going to find his beginning. So when he is walking, he starts here at 50. So walking, he starts at 50. So that goes here. He goes to position 0 because he's starting at 50. He's going to 0. And we're going to say like time. So it's now at 8 seconds, right? 8 seconds has elapsed when he's at 50. And remember, it took him 40 seconds overall. So we're at 48 now. Okay, so I do that's negative 50 over 40. Divide that out. You will end up with negative 1.25 meters per second. I have a feeling there's going to be some confusion with that, but hopefully if you have any questions, you'll ask me, okay? The idea is, remember, he's walking to the left. So if the original spot is here, since he's walking to the left, it's going to, even though he's to the right of it, he's still walking to the left, it's going to be negative, which it ended up. Now, for the complete round trip, so let's think about his velocity average for the whole thing. I'm just going to put round trip. Look at all these labels. It almost becomes obnoxious. So where does he start the problem? Well, he starts the problem in position 0. Where does he end the problem? Well, he ends the problem at position 0. What's the beginning time of the whole problem? 0. What's the end time of the whole problem? 48. So we end up with 0 over 48, which oddly enough is 0 meters per second as his average velocity. Oh, that's a fun little shape. I'm going to keep it on there. But the idea is velocity is concerned about displacement. So when you think about his whole trip, phone call, when you think about his whole trip, he's ending and starting at the same spot. So since that's displacement, his velocity is going to end up being 0. Something I did on my notes that you can do on each one of these, I identified, like on part A, his sprinting, I wrote x2 is 50, x1 is 0. And then on the walking route one, I wrote x2 is 0, x1 is 50. That might help some of you just kind of like wrap your head around what's going on here. So like this one, x2, he ended at 0, x1, he started at 0. I don't know if that's helpful or not. If it is, please feel free to write all those little pieces down. All right, so the bell rang. I'm out of here. We'll pick up with another video.